Okay, so a lot of this is review. We're going to take a look at inverse relations today, talk about what it means to be an inverse, look at the test to determine if two relations are inverses of each other. And then we'll extend this a little bit. You've done this stuff, but you've only done this stuff probably for linear functions. We're going to look at some nonlinear functions, at polynomials and things like that. But it's the same principles apply. It's not much of an extension. Okay, so first of all, inverse, what's a relation? A relation is anything that could be graphed. A relation is just, if I've got a relation involving x's and y's, it means that I could come up with some equation, and if I wanted to know the y values that go with x values, I could plug in values for x and find out what y equals, the y's that go with them, right? Now relations could be functions or they might not be functions. And we'll look at that in a little more detail here in just a little bit. So an inverse relation, if I've got some relation, some ordered way of mapping, I put in x values and the equation tells me what to do to get the y values. If I've got some relation and I want to find the inverse, here is what that really means. The inverse just maps the output values of the original onto the input values of the inverse, okay, and vice versa. So what it's saying is we're just flipping the x and y values. That's it. The x values of the original become the y values of the inverse, and the y values of the original become the x values of the inverse. For example, let's say I've got this original relation. I've just got my domain is this. I've got only 5 values of x in my domain. These 5 values, that's it. Then that means that for the inverse relation, what used to be my domain, the values of x, becomes the range, the values of y. Okay? And my original range, the values of y in the original, become the values of x, the domain of the inverse. Okay, now watch what happens if I plot these graphs. If I graph the original relation, and these are just ordered pairs, aren't they? If I think of, like for example, this right here, this guy right here is just the ordered pair, negative 2, 4, right? I go back 2 and up 4 to get to that point. So if I plot these, look what happens. Okay, here's the xy axis. Now, there's the graph of the original relation. These are the 5 points associated with these 5 ordered pairs. When I graph the inverse, watch what's going to happen here. Instead of going left 2, and up 4, I'm going to go, if I look at this corresponding ordered pair in the inverse, I'm going to go right 4 and down 2, right? And so notice what it does. It actually ends up being reflected over the line y equals x. That's the line of reflection. And this one ends up being right over there, right? It's just reflected over that line. So where's this guy going to end up? Well, it's going to get reflected over the line. It's going to get reflected over the line and end up down here. Right? What about this guy here that's actually on the line of reflection? It's going to stay put. This guy down here is going to get reflected over, and this guy's going to get reflected over. Okay? So that tells us something important. The graphs of inverses are mirror images of each other, reflected over this line, this diagonal line, y equals x. Okay, just a line through the origin with a slope of 1, right? There is an easier way to do this, though. It may not sound easier at first, but trust me, this is easier. An easier way, it's kind of hard visually to reflect stuff over a diagonal line. It can be done, and if you practice it, you can do it. But it's much easier to reflect stuff over horizontal and vertical lines. And so there's a 2-step recipe that you can use to replace reflecting over the xy line x equals y, over the diagonal line. These are the 2 steps. If you take the original, blue in this case, and you rotate the graph 90 degrees counterclockwise, so that's the first step. So first we do this whole thing, like this guy right here, for example, is going to get rotated down. Right, it's going through this angle of 90 degrees. Rotate 90 degrees counterclockwise, and then whatever you get after you rotate it 90 degrees counterclockwise, you're going to reflect over the y-axis. Those two steps are actually easier to do than that one reflection over the diagonal line. So once again, rotate everything 90 degrees counterclockwise, and then reflect everything over the y-axis. Okay? We'll look at that in a little bit. We'll see how that works. It's really pretty easy to do. Okay, so there's our graph of the inverse. Okay, how do we find inverses? And you've done this before. What's our recipe for finding inverses? If I start off with something like this, let's say. Okay, and I'm going to write it a little differently to start with. Let's write it as, instead of as y, what if it had started off as f of x equals 2x minus 4? Now go back to Algebra 1 here and see if you can remind us, how do we find the inverse of that? What do we do first? It's the first step always. Yeah, we'll get you started. You always write it in terms of x and y. So the f of x we're going to replace with a y. Now what? I want to find the inverses. What was my recipe for an inverse? What did it mean to be an inverse? Opposite in what way? What did I do? Okay, well, I switched the x's and y's, right? That's all we did was flip the x's and y's. So do that. Exchange the x's and the y's. So this becomes an x, that becomes a y, and now all I do is solve for y, and that's the inverse. So what are the two steps I would do in order to get that y by itself? What do I do first? Add 4, then divide by 2. So if I do that stuff, don't I get y equals x plus 4 all over 2? Right? And if I want to split that up into two separate terms and make it look like mx plus b, I can do that too. I could just make that 1/2 x plus, what if I split it into two separate fractions? X over 2 becomes 1/2 x. What's 4 over 2? 2. Yeah, so there's my inverse, right? Okay, so once again, all you do, the recipe for finding an inverse, write it in terms of x and y, flip the x and the y, solve for y. Okay, and the new y is your inverse. Okay, and so there it is. That's what we did, right? There's our answer. Okay, so there's our inverse. Okay, and we'll practice that in a little bit with some harder functions. Now here's the other thing that you got to be the test for inverse functions. If f and g are inverses of each other, then you can always check to see if that's true. If we're told that they're inverses of each other, if they are, they have to undo each other. Inverses are sort of like opposites in a way. Inverses undo each other. And you've actually done this stuff without knowing it in the past. You've done things like, for example, if you were solving, for x here. What if I had 2x minus 3 equals 4? You've done some inverse stuff here. What's the first thing you do? I'm trying to get the x by itself, so I've got to undo all the stuff that's being done to the x over here. What's the first thing that we do to undo that x, to get it by itself? Add 3. And we add 3 because adding 3 is the inverse process of subtracting 3, right? So we get 2x equals 7, and then now what? Divide by 2, because dividing by 2 is the inverse process of multiplying by 2. So you're already used to this. And even if we went one step further, and what if that was an x cubed, right? Then we would have said x cubed equals 7/2, and what's the inverse process of cubing? Cube rooting, right? And so we would have had x equals the cube root of 7/2 for our answer. So you're already used to this idea. You've done a ton of this year. Okay, so we've just got to see if these two relations undo each other, right? So let's take a quick example. What if we've got these guys. Okay, f of x equals 2x minus 4 and g of x equals 1/2 x plus 2. Now let's remind ourselves what it means to be a relation like that. Let's take the f of x for a second and just practice with this. If f of x equals 2x minus 4, what is that really telling us? That's really telling us what we're going to do to all of the input values, the values of x, that we feed this function, right? How would you describe that? When I put stuff in, what does f do to it? What's it do to it? Well, let's try an example. What if I put in f of 2? What's the answer going to be? 0. How'd you know that? Oh, okay, so whatever I put in for x, I multiplied by 2 and then subtracted 4, right? So that's what this function f is telling me to do. Whenever I input something, I'm going to first multiply by 2 and then subtract 4 from that, whatever I got, right? So 2 times 2 minus 4 gave us 0. What is f of a equal to? Yeah, we don't know what a is, but I know the answer is going to be 2a minus 4, right? Does that make sense? What is f of g equal to? Okay, now let's take that last one and let's just change it ever so slightly. Instead of making that f of g, let's make it f of g of x. Okay, so what is that? If I'm feeding f the function g of x, what am I going to do to g of x? What do I always do? Okay, I'm going to multiply whatever I'm inputting to f. I'm going to multiply it by 2. So I'm going to get 2 times, now I got to put this in parentheses because it's a bunch of stuff that's being multiplied by 2, right? So all this goes there because that is g of x, isn't it? Right? And then at the end I've got to subtract 4.
And why is it multiplied by 2?
Because that's what the function is telling me to do. Whatever I input, I'm going to multiply by 2, right? Okay. So what does that work out to be? If I just simplify that, if I do the math, what do I get? I got to distribute the 2, right? So what's 2 times 1/2 x? X, right? Good. 2 times 1/2 is 1 times x, so that gives me x. 2 times 2 minus 4 equals, no, x. Yeah, those cancel, so I just get x, right? So f of g of x equals x. Check. So what does that mean? Well, that means that f of x just undid g of x, right? When I put g of x into f of x, it completely undid it and just gave me back an x, right? Now we got to see if it works the other way also. So that way did work. Okay, so what is g of f of x? Well, what is g of x asking us to do? It's asking us whatever I'm putting in, I'm going to, what do I do first? What do I do first? What do I do to the x first? Times it by 1/2. Hey, you guys, quit being so squirrely. Turn around.
You can't listen to math by looking that way.
You can't. So if I'm going to first multiply by 1/2 whatever I put in, and then I'm going to add 2, right? So that's going to give me 1/2 times all that stuff, because all that stuff is g of x. Whoops, sorry. F of x. So I want f of x. I go back. Sorry. I'm doing g of f of x. So here's my f of x right there. That's what I want to put inside. And then at the end I got to add 2, right? So there it is. G of f of x equals 1/2 times f of x plus 2. If I distribute the 1/2, what do I get? I'm going to have 1/2 times 2x is x. 1/2 times -4 plus 2 equals x, right? Those add to 0. Okay? So it worked. Okay, so f of g of x equaled x, and g of f of x equaled x. And so that tells me that these are inverses of each other. Okay? And by the way we write inverses then, if the inverse of f of x is equal to that. That's our notation for inverse. A little strange. It does not mean to the -1 power. That's not it at all. It means, and we do this a lot in math, we kind of recycle our symbols, but you just got to think of the context. We're not talking about flipping something. We're talking about literally switching x and y and solving for y. The way we would say that is the inverse of f of x, or the other way we could say it is f inverse. Okay? Either way. Okay, so what do we do about this one? Find the inverse of f of x equals x squared. Now, actually, I'm going to, well, no, we'll do this. If I want to find the inverse of f of x equals x squared, let's do that on here. If I want to find the inverse of f of x equals x squared, well, x squared just looks like this, doesn't it? Right? I'm going to get rid of one thing here for a second, too. Let's get rid of that. Everybody agree that that's just a parabola, y equals x squared? Now, if I want to find the inverse of that, I gave you a recipe for doing that. Right? If this is the diagonal line, y equals x, it's got to be the reflection of that over that line. That's a little hard to do, though, so let's do it in 2 steps. Let's take the blue parabola, and first of all, let's just rotate that 90 degrees counterclockwise. Okay? And then what do I do? Reflect that over the y-axis. Good. Okay, so conveniently, I've got that done already. And so we end up, if I reflect the gray one over the y-axis, don't I get the red one? Right? Okay, so those are inverses of each other then, the blue and the red. Okay? If I flip the x's and y's, what do I end up with? X equals y squared. Okay, or another way of saying that would be y squared equals x, right? Okay, so that is a sideways parabola. Now, is the blue parabola that we started with a function? It is. You're right, it is. How do we know that it is? Okay, it passes the vertical line test. Any vertical line that passes through the blue parabola only intersects it once. But is the red parabola a function? No, it's not. It's going to intersect any vertical line twice, and so that's not a function. Okay, now, this is really cool that it works out this way. Math gods are looking after us. If we solve for y here, I want you to tell me, what result do we get? If I solve for y there, y equals what? How do I get that y by itself? Okay, I square root both sides, don't I? Right? Now, look what happens here, very carefully. If I square root this thing, though, it's not just equal to the square root of x. What do I have to put out front? The square root of, no. Now, you guys know this. If we were solving, now tell me what would happen here. If I had x squared equals 4, what would x equal? Not just 2. Plus or minus 2, right? I'd have to put that plus or minus there because, right, does that make sense? Because that was even, We took an even root, right? Remember the rules? And so here, if I solve for y by taking a square root, an even root of both sides, I have to put a plus or minus out front. Let's make the plus green and the minus pink. Okay, there's a reason for that. Why did we do that? Well, if I look at what is the square root of x graph look like? The square root of x is just the top half of this red graph. Okay. What does minus the square root of x look like? That is just the bottom half of this graph. Now pay close attention because this is so cool. Look what it did. When we solved for this, the math gods gave us back two separate answers, plus the square root of x or minus the square root of x. If I look at either one of those two by themselves, if I just look, for example, at y equals positive the square root of x, is that a function? It is, right? Just the green one by itself does pass the vertical line test, doesn't it? Right? What about the pink one? By itself, if I take the graph y equals minus the square root of x, by itself, it is also a function. So what this did is it carved it up into two separate functions, each one of which works by itself. Okay? But the green one, if I think of which part of the original blue graph gave us the green graph, let's make that one orange. It's going to get a little complicated. Which part would it be? Would it have been the left part or the right part? The right part. Okay. So this would have been the one that goes with the green, right? Does that make sense? Now, how could we say that? How could we specify that? Well, if I went up here to the original function, I would have had to have said, okay, this is the graph we're interested in, but we're only going to take the x values that are greater than or equal to 0. We're not going to graph any of this function for values of x less than 0. So we would have to specify something like that. Okay, if I restrict that original domain to only be the orange part, then its reflection is going to be only the green part, and that is a function, right? Now, on the other hand, if I want to find the part that goes with the pink graph originally, that would have been the left half of the blue graph, wouldn't it? Right? Everybody see that? Okay, so I'm running out of colors here. That one's going to be, what is that one going to be? It's going to be, I got blue. White's going to be pretty tough. It's going to be gray. Okay, so this side, if this side is kind of dark gray, that would be the part then that would go with the restriction that x is less than or equal to 0. And the gray would go with that. Okay? Now, that worked out great though, didn't it? Because I want you to see something here. Look how we could have started with the original. We didn't even have to go through this whole process. We could have instead, whoops. We could have just done this. If I knew that my original function were f of x equals x squared on the interval x is less than or equal to 0, we can play the same game we were playing before when we solved for the inverse. We're just going to swap the x's and y's, right? So we'll write this in terms of y. Y equals x squared, but I got to include that part, that restriction, x is less than or equal to 0. Now when I flip the x's and y's, what do I end up with? Well, x equals y squared. And what does this become? Y is less than or equal to 0, right? Okay, if I turn this around so that becomes y squared equals x, and I do the math here, if I solve for y, don't I get y equals plus or minus the square root of x, right? But if y has to be less than or equal to 0, which of those two signs am I going to keep? The minus. You see that? That because of this condition right here, we're going to keep the minus and forget the positive. We didn't even have to graph those things, right? This condition up here told me which one of these two answers we were going to keep. See how that works? Isn't that cool that it does that? Right? And so if we had a problem instead, if I had one like this, what if I had, I started off with y equals 2x to the, well, hang on, yeah, 2x to the fourth, how about, okay? And we're only interested in values of x that are greater than or equal to 0. If we solve for the inverse this time, we get x equals 2y to the fourth, y is greater than or equal to 0. If I solve for y there, what do I do first? I'm going to solve for y. What do I do first? I'm just following order of operations in reverse if I'm isolating, right, or solving. So no addition, there's some multiplication or division I gotta deal with. Divide by 2, okay? Right, so I get y to the fourth equals x over 2 exponents. What do I do now? Fourth root. So y equals, it's even, so I need a plus or minus, don't I? Plus or minus the fourth root of x, but if y is positive, if y is greater than or equal to 0, which one are we going to keep? The positive, and we cancel the negative. So our answer is just positive fourth root of x, right? Now it gets easier if you do odd powers. Odd powers are a piece of cake, right? Odd powers, if I want to solve here for, if I want to find the inverse of this, right, I get the equation y equals negative x cubed. If I flip the x's and y's, doesn't that just become, whoops, doesn't that just become x equals negative y cubed? Okay, but because that's an odd power, isolating y becomes much easier. What do I do to isolate y first? What do I do to isolate y first there? Okay, I got a multiplier divide by negative 1. So negative x equals y cubed. And now what? How do I undo that power? Cube root. Okay. So y equals the cube root of negative x. Do I need a plus or minus? No, I don't, because it's odd, right? And look what happens. The original function, right, if I reflect that over the axis, look what happens here. If I rotate it 90 degrees first, right? I rotate this thing 90 degrees counterclockwise, and then I reflect that over the x-axis. Here's my red graph. That's not my red graph. That's my red graph. Right? Make sense? We can get rid of this guy now. We don't need him. Okay, the original red or the original blue graph is a function, right? So is the red graph. They both pass the vertical line test, don't they? Right? So there are two important things that came out of that. We know right away we can breathe a sigh of relief. If I've got an odd power, there's no plus or minus to deal with. I know it's going to work out, right? And the other thing is I knew that I was going to get a function when I did the reflection, right? Now, could we have predicted here? Let's go back and look in hindsight. How could we have maybe predicted that this original blue function, this blue function here, was going to produce an inverse that did not pass the vertical line test? Is there a test we could have done on the original blue function that might have told us, okay, when we rotate this thing and reflect it over the y-axis, it's not going to pass the vertical line test? What do you think? Yeah, we could have done a horizontal line test. Now, what does the horizontal line test do? The horizontal line test just predicts whether the inverse is going to be a function. The original blue function passed the vertical line test, so it is a function, but it would have failed the horizontal line test. Any horizontal line would have intersected it more than once. Well, here's what you're thinking is, if a horizontal line intersects the original more than once, then guaranteed a vertical line is going to intersect the inverse more than once, okay? And so there's a way to predict whether we're going to end up getting an inverse function or not. Whether the inverse will be a function or a non-function. Okay, so let's just summarize what we just talked about, because that's it. That's the whole ball of wax right there. skip ahead a little bit, whoops. Okay, so if we look at these two functions here, here's what we got. If we look at this original f of x equals x squared, notice that its inverse is a sideways parabola, and so it is not a function, right? The inverse of f of x is not a function, but the inverse of x cubed, if f of x is x cubed, the inverse is a function, right? And what we find then is what we just came up with, is the idea that we get this horizontal line test. If no horizontal line intersects the original, then we're guaranteed that the inverse is going to be a function. It's going to pass the vertical line test. Make sense? Okay. That's it. I've got an assignment for you on this. The assignment, let me just kind of tell you what it's going to be. I spent a lot of time and built some questions.
3 questions?